Hello friends, in this lecture we are going to discuss about real lattice and reciprocal lattice. Let us first briefly discuss why do we need the concept of lattice. So we started our discussion with free and independent electron gas model, and we ignored electron ion and electron-electron Coulomb interaction. First we discussed the classical free electron gas model, and then we discussed quantum free electron gas model. We have found that certain anomalies observed in classical free electron gas model, like the magnitude of the heat capacity, was resolved by using the quantum free electron gas model. However, certain other anomalies like sign of the Hall coefficient could not be resolved even after using the quantum free electron gas model. Thus, we concluded that the sign anomaly of Hall coefficient cannot be understood using free electron gas model at all. Thus, we need to include the electron-ion interaction. And positive ions arranged in lattice provides a periodic potential, and we need to solve the Schrodinger equation in the periodic potential. So before we do that, let us briefly understand the concept of lattice in this lecture. Picture of copper and sodium chloride crystal is shown here side by side. This is how the copper atoms are arranged in a copper crystal, and this is how sodium and chlorine ions are arranged in a sodium chloride crystal. Do you find any similarity between the two? Now, let us focus on these small points, right? In case of copper crystal, what we do is that we place a copper atom in place of all these small points. But in case of sodium chloride, what we are doing is that we are placing a sodium chloride molecule in place of all these small points. So you can see that in place of every small point, we are putting this sodium chloride molecule. Note that these are not really molecules, but these are like just the sodium and chlorine ion pair. Now, instead of the actual atoms or ions, if we consider only the imaginary points, then what you get is a lattice. And this shows the underlying periodicity of the crystal. Thus, you see that this copper and sodium chloride, both of them have same underlying periodicity. And this is shown by the lattice points. The periodic array of points, this is called the lattice, right? This is what is shown here, right? And this depicts only the geometry of the underlying periodic structure, regardless of whatever atom or molecule we put at every lattice point. We can say that a crystal, it is made of two things, lattice and basis. So we have these imaginary lattice points, and what is the basis? In case of copper, the basis is just a single copper atom. So that means at each imaginary lattice point, we put a copper atom, and that will give me the copper crystal. And in case of, if we want to build the sodium chloride crystal, what we have to do is that in place of every lattice point, we have to put a sodium and chlorine ion pair like this, and that will build the, so that is the basis, right? In case of sodium chloride, the basis is a pair of ions, right? Sodium and chlorine. Okay, so that is how you get a crystal. Now, there exists a special class of lattice, and those are known as like Bravais lattice. There are 5 Bravais lattice in 2D and 14 in 3D. Let us briefly discuss about them. A 2D crystal has 3 types of symmetries: translation, rotation, and reflection. Only 5 types of rotations are possible if we want to preserve translation symmetry. And Those are like twofold. Twofold is 180-degree rotation, threefold 120-degree rotation, fourfold 90-degree rotation, and sixfold. That is 60-degree rotation. I didn't list out the other possibilities like one-fold. That is a 360-degree rotation, which does not give you anything new. We shall generate all possible 2D Bravais lattice by combining translation with rotation and reflection. Before we start, note that we need two non-collinear vectors to define a 2D lattice. So let us take this case, right? So we take the first vector, right, to be A1. And what we need another vector to define a 2D lattice. So first combine translation with twofold rotation, right? So in this case, if we apply twofold rotation, then what we get is we get this vector, right? We get some vector which is in this direction, right? Because I have rotated it by 180 degree, right? But this does not give me another non-collinear vector, right? So we are getting the same vector but in the opposite direction. So what we need to do is that we can just put the other vector, right, in a manner that such that it is non-collinear, right? So we can just take this, right? So let us put A2 here, correct? And then what we see here, right? So in this case, there is no restriction on the second vector, right? So that means A1 is not equal to A2, and they have some angle, and then the angle is also, there is no restriction. Only the thing is that it cannot be 180 degree, because the 180 degree will give you the same vector. That will not give me two non-collinear vectors. So A1 angle A2 is equal to some general angle alpha, which cannot be equal to 180 degree, right? So this is the angle alpha. Next, we take a vector, again A1, and then what we do is that we combine it with threefold rotation, right? So threefold rotation is like the 120 degree rotation, right? So I get the second vector in this direction. So that means the rotation by 120 degree, right? So this angle is now fixed 120 degree. That already gives me another vector which is non-collinear. And in this case, how these vectors are related. So now A1, the magnitude of A1 is equal to magnitude of A2, and the angle between them is one, that is also fixed, that is equal to 120 degree. Now, I just leave it as an exercise for you to verify that if we try to combine the translation with sixfold rotation, we get the same lattice. So next, what we do is that we take this lattice vector A1, and then what we apply is we apply fourfold rotation, right? So in that case, the second vector is along this, right? So this is A2, and this angle is 90 degree. So that means, again, we see that we already have, just by the rotation, we already have another vector which is non-collinear, right? So in this case, the lattice vectors, they are related by A1, magnitude of A1 is equals to magnitude of A2, and the angle is given by 90 degree. So now we have exhausted all possible combinations of translation and rotation. Right? Now let us combine translation and mirror. So again, we take the first vector along this direction, and then what we do is that we put a mirror plane. So we put a mirror plane which is not perpendicular to this vector. Okay, so now if we do that, then what happens is that because of this mirror plane, right, I get, so this vector gets reflected, correct? Then that means I get another vector which is here, correct? And that already gives me the second vector, which is like non-collinear. So in this case, how these translation vectors are related, so they are related by the magnitude of A1 is equals to magnitude of A2, and the angle between them can be in general angle. A1 angle A2, this is equal to some general angle alpha, right? So this we just call it as alpha. Okay, so we are done with this. Now we can put the mirror in some other way. For example, what we do is we can put the mirror perpendicular to the first vector, correct? So let us put the mirror in this direction, okay, which is perpendicular to the lattice vector A1. And then we see that if we do it in that way, then I get another vector, correct? But this is not non-collinear. So that means this will not give me another vector which is non-collinear. And then we have to put the second vector in some direction. So, and then I just leave it as an exercise for you to prove that the only direction in which we can put the other vector is along the mirror. If we try to put in any other direction, that will give me a third vector, and then there is some redundancy, and then things are not well defined, correct? So we cannot do that. The only place we can put the second vector is along the mirror, and then that gives me this relation, correct? A1 is not equal to A2, right? And then angle between them, A1 angle A2, that is fixed, that is equal to 90 degree. Thus, we have generated all possible Bravais lattice in 2D by combining translation with rotation and combining translation with reflection symmetry. Now, this is the complete list, and we also have derived the relation between the two lattice translation vectors, their magnitudes as well as the angle. So the first one where this has the least symmetry, right? So this is like the magnitudes are different of the two vectors, and the angle between them is also some general angle alpha. So this is known as the oblique lattice. The second one is known as the rectangular, and in this case, the magnitudes are different, but the angle is fixed. The third one is diamond, where you have the magnitudes of the two vectors are equal, but the angle is general. The fourth one is square, where the magnitudes of the two vectors, the magnitude is equal, and the angle is also fixed, equal to 90 degree. And then hexagonal lattice is again the magnitudes are equal, and the angle can be either 60 degree or 120 degree, and they are same. In case of 3D, we are not going to derive the lattices, but using the same principle, we can derive them. Here is a list of 7 possible crystal systems in 3D, and you see that the names are like triclinic, monoclinic, orthorhombic, tetragonal, trigonal, hexagonal, and cubic. So in case of this triclinic, this has the least symmetry, and then you see that we need like 6 cell parameters to describe them. The magnitudes of all the lattice translation vectors, now there are like 3 of them. So their magnitudes are different, and the angles are also general. And then as we go down, then we see that the cubic has the highest symmetry, and we need only one lattice parameter in this case, and that is just because lengths of all the lattice translation vectors are equal, and the angle is also fixed and equal to 90 degree. We already have discussed about lattice in 2D and 3D. Let us now discuss about reciprocal lattice. We keep our discussion very general by choosing a triclinic unit cell having least symmetry among all. First, note that, so this is the cell, right? So we have like A1, A2, and A3. These are the 3 lattice translation vectors. So their lengths are not equal, and angles are also general. The volume of the unit cell is given by A1 dot A2 cross A3, right? So A2 cross A3 is the area of this base, and then if you just take a dot product with A1, that will give you the volume of the unit cell. Now find a vector perpendicular to A2, A3 plane, right? So this is the plane, the plane at the base. And then what we can do is that we know that if we take a cross product of these two vectors, right, A2 and A3, that will be perpendicular to this A2, A3 plane. So let us do that. So we know that the vector is given by A2 cross A3, right? So this is the vector perpendicular to this plane. So B1, it's like A2 cross A3. So we take this vector, we multiply it with 2 pi and divide it with the volume, correct? A1 dot A2 cross A3. So this is the definition of B1, right? So B1 is a vector which is perpendicular to this A2, A3 plane, and then we have like multiplied it with some constant and then with the volume, and then we will see that what will be the magnitude of the vector. At the moment, we just know the direction of this vector, right? So this direction is perpendicular to A2, A3 plane. Then we have another vector B2, which is perpendicular to A1, A3 plane. And then we have another vector B3, which is perpendicular to A1, A2 plane. Now let us convince ourselves that the B vectors have a dimension of 1 over length and its magnitude is inverse of interplanar distance. So let us take B1, right? And then we see that this height of the parallelepiped, right? This is like D23, correct? That is given by A1 dot n hat 23, where n hat is a vector. This is the unit vector, correct? N hat is the unit vector perpendicular to the A2, A3 plane. So what we do is that we just take the vector which is perpendicular to A2, A3 plane and divide it with its magnitude. So that will give me the unit vector, right? And then we see that the height of the parallelepiped, that is given by A1 dot n hat 23. And then we just place in place of n hat 23, we just place this A2 cross A3, divide it with its magnitude. We rewrite the B1. Okay? So B1 is equal to 2 pi. And A2 cross A3 is a vector, right? So we just take its magnitude, and then n hat 23 is its direction. And then, of course, this is divided by the volume. So n hat 23, it's already there. And then if I just divide A2 cross A3 by its magnitude, right, then I get this n hat 23, right? If I take a dot product of A1 and the unit vector in this direction, right? So that will give me the projection of A1 along this n hat 23, right? And that is equal to the height, or that is equal to the spacing between these planes, right? So for example, right, we can take this to be the A2, A3 plane, and then we can take another plane which is parallel to this, correct? Correct. So if we take this set of planes, right, then what we can define is that what is the distance between, distance means the perpendicular distance between these set of parallel planes, and that will be given by D23. Okay. So we can write B1 as this, right? So this is like 2 pi divided by D23, which is the interplanar spacing between two adjacent parallel A2, A3 planes, times the unit vector, right, along in this direction. So that means we already know the direction of the B1. So now thus we have like found the magnitude of B1. So magnitude of B1 is given by 2 pi divided by D23. That is 2 pi divided by distance between two A2, A3 planes. Thus, starting from the lattice vectors A1, A2 and A3, we have constructed three vectors B1, B2 and B3. Now, We can fill space using A1, A2, A3 as basis vectors. Correct? So that means if we take this A1, A2, A2, A3 and we just keep repeating them in space, then we are going to fill the entire space. Correct? In this case, it is not too difficult to understand the space filling, as all these vectors like A1, A2, A3, these has the dimension of length. Now you see, I have also drawn the B1, B2 and B3 vectors. So, and again you see that if I just repeat these vectors, right, then we are going to again fill the space. But now in this case, what type of space are we filling? To understand this, let us focus at the dimension of B vectors. Okay. So we know that this magnitude of Bi is equals to 2 pi divided by distance between two AJ AK planes. And this implies that the B vectors, they have a dimension of 1 by length. Remember that when we discussed about the K space in case of free electrons, right? The vectors in K space also had the same dimension, right? That is the dimension of 1 by length. So since B vectors have a dimension of inverse length, space filled by B vectors is known as a reciprocal space. We call this the lattice formed by A1, A2 and A3 as the real or direct lattice, and lattice formed by the B1, B2, B3. This is known as the reciprocal lattice. Now, we can just take a linear combination of B1, B2 and B3 that will give us a vector in the reciprocal space. For example, if we take a combination of A1, A2, A3, that will give us a vector in the real space. Similarly, if we take a linear combination of B1, B2, B3, that will give us a vector in the reciprocal space. We know that wave vectors in K space, they have a dimension of 1 over length, and now G has also the same dimension of 1 over length. So that is why we can argue that this G is also a wave vector. So far, we have defined the basis vectors of real lattice given by A1, A2, A3, and the basis vectors of the reciprocal lattice given by B1, B2, and B3. Now, a general vector in real space, they can be expressed in this form. R U V W is equals to U times A1 plus B A2 plus W A3. For example, you can take this point, correct? And then you see that how do I reach this point starting from the origin, right? So that means, so this is the origin, correct? So I move along A1 by 1 unit. I move along A2 by 1 unit, and I move along A3 by 1 unit, right? So that means this is the 1, 1, 1 point in real lattice. Similarly, we can write general reciprocal lattice vector as GHKL. And this is equal to H times B1 plus K times B2 plus L times B3, where H, K, L are integers. Again, right? So for example, let's take this point in the reciprocal lattice. So what we do is that we move along B1 by 1 unit, we move along B2 by 1 unit, and we move along B3 by 1 unit, and then this is the 1, 1, 1 point in the reciprocal lattice. Now, can we take a dot product between R and G? We have to know how does AI dot BJ look like, right? Okay, so let us take some examples. So let us try to calculate A1 dot B1. So A1 dot B1. So we are trying to find this, and then let us calculate this. Okay, so A1 dot B1 is 2 pi, and A1 is this, and what is B1? B1 is dot A2 cross A3, and then I divide by A1 dot A2 cross A3. Correct. And then what you see is that we have the same term in the numerator as well as the denominator. So this we just write it as, right? So this will cancel out, right? And then we just get a term of 2 pi. Now let us calculate A2 dot B1. In this case, what we see is that we have this factor of 2 pi, and then we have A2 dot A2 cross A3 divided by A1 dot A2 cross A3. Now you see that A2 cross A3 is a vector. Since this is a cross product, this is a vector which is perpendicular to both A2 and A3. So in that case, I am taking a dot product between two vectors which are perpendicular to each other, and so that means this term will be 0. Correct? So that means A2 dot B1 is equals to 0. By the same logic, we can just show that A3 dot B1 will also be equal to 0. Right? Remember that what we know is that, so by the way we have constructed B1, B2, and B3, what we have is that we know that B1 is perpendicular to A2 and A3. Correct? Because we know that B1 is a vector which is perpendicular to this A2, A3 plane, and this vector A2 and A3, they are lying in this plane. So that means B1 is perpendicular to both A2 and A3. And that is why this is not surprising that the dot product is 0. But it is not necessarily true that B1, right? So that is B1 need not be parallel to A1. Okay. They can be in some special cases, but if we take a general case, they need not be parallel. Thus, these three equations, right, we can write in a nice compact form in this way. Okay, so AI dot Bj is equals to 2 pi delta ij. So delta ij is the Dirac delta. So that means delta ij is equals to 1 when I is equals to j, and delta ij is equals to 0 when I is not equal to j. Now we can just use this fact, and then we can take a dot product between R and G. So R dot G will now look like UH A1 dot B1, correct? And A1 dot B1 is equals to 2 pi, correct? And now you have all these other terms, right? A1 dot B2, that will be equal to 0. A1 dot B3 will be equal to 0, and so on. So that means only the terms like A1 dot B1, A2 dot B2, and A3 dot B3 will be non-zero. Rest of the terms will be equal to 0, and they are given by UH plus VW plus KL. And since VW and HKL, all of them are integers, we get something like 2 pi L where n is an integer. So this is how the dot product between R and G, right? R is a vector in the real space and G is a vector in the reciprocal space. So this is how their dot product looks like. Since R dot G is equal to 2 pi n, we can just take exponential, right? We can just write it as e power I G dot R is equals to e power I 2 pi n. This is equals to 1. Now let us take some plane wave e power I k dot R, right? So let us take this expression and let us examine whether this has the periodicity of the real lattice. Let us see that what do we need for it to have the periodicity of the real lattice, right? So what we need is that e power I k dot R, right? For it to have the periodicity of the real lattice, what we need is that e power I k dot R plus R, where R is a vector in the real lattice. R vector in real lattice. And then we know that R has this form. Okay. And now what do we need for these two things to be equal? What we need is that e power I k dot R has to be equal to 1. But we know that for some general wave vector k, this is not true. Correct? This is not true for some general wave vector. So thus, if we take some plane wave which has this form e power I k dot R, then that does not have the periodicity of the real lattice. However, now if I take the wave vector to be capital G, then let us see that what happens, right? So we have also defined like some, we know that G is some wave vector, right? So that means if we just take k equal to G, right? The wave vector we take to be equal to G. In that case, what do we have? In that case, we need to satisfy this equation. Okay. And then we see that this equation is satisfied because we know that e power I g dot R, we just have derived it here, e power I g dot R is equals to 1. So that means if we take the plane wave with wave vector equal to G, then in that case, such plane waves have the periodicity of the real lattice. Thus, so G, these are like special wave vectors which will give us some plane waves having the periodicity of the real or direct lattice.